Okay, question 5 is now asking something slightly different. It's asking for a Norton equivalent circuit, but it's gone back to having at least one independent source, right? So our V2 here is an independent source. So you've got to do two things. The way I decided to solve this one is through using open circuit voltage, short circuit current. So I did it that way. So the first thing I do is remove the load resistor. That's what I've done here, right? I've whited out the load resistor. And so the open circuit voltage is really the voltage at this point here, because there's no current flowing through R4. So I just need to do that. So it's a two mesh analysis problem. We could also do it using nodal analysis if we wanted to. That'd maybe be okay. It'd be a 3-node nodal analysis, but we'd already know what node A would be. The leftmost node would be the same as V1. But I decided to do it using mesh analysis. Okay, so mesh analysis. First of all, I1 is minus V1. V1 is 2000 I naught. So our control variable is here, the current through R3. So that's 2000 times I2. The only current flowing through R3 is I2. So minus 2000 I2, and then R1 is 4K, so that's 4000 I1, and then R2 is 5K, so that's 5000 I1 minus I2, because I2 is flowing in the opposite direction through R2. And all of that equals 0. That can come down to 9000 I1 minus 7000 I2 equals 0. And then we can do the mesh for I2. We get 5000 times I2 minus I1 for the voltage across R2. And we get minus 15 because we're going into the negative side of V2. And then we get R3, which is 3000 times just I2. There's no other current flowing through there because we've got an open circuit on the right hand side. And that comes down to minus 5000 I1 plus 8000 I2. And we can put that into a matrix like that and get our answer for the Thevenin voltage, right? So of 10.95 volts. And then we need to remember to solve the circuit, we need the open circuit voltage and the short circuit current. So to find the short circuit current, I've redone it, and I've just said we're replacing RL, the load resistor, with a wire, and that's got the short circuit current flowing through it. And then we do the same analysis again. Now the analysis this time is a little different because now the control variable has both I2 and minus ISC, right? So we're going to get a minus ISC up here. Everything else should be the same, but just be aware of that. And then I2 is pretty much the same, except again we're going to get an I2 minus ISC going through R3. And we didn't have this mesh before, but it's nothing more than the voltage across R3 plus the voltage across R4. And that ends up minus 3000 I2 plus 8000 ISC. And then we can put that, it's a slightly larger equation this time. It's a 3 by 3 because there's 3 unknowns, there's 3 mesh currents. And if we do all that, then we can find the Norton current. And the Norton current comes out to be 1.653 milliamps. And then in order to find the Thevenin or Norton resistance, remember Thevenin resistance equals Norton resistance, we can just divide the Thevenin voltage by the Norton current, and our Thevenin or Norton resistance is 6,624 ohms. And if I plug that in to WebWork, then everything comes out nicely, right? So there's my current, there's my Norton resistance, and then to find out what the load is, what I can do is, let's go back here, what I can do is I can say, right, we've got our Norton current and we've got our Norton resistance. Now we've got our load resistor, right, which is just that. So the voltage output is just going to be the current times Rn in parallel with the load resistor. Okay, because the equivalent resistance of Rn in parallel with the load resistor is just that. And if we look at the MATLAB, that's all I've done. I've taken 1 on RTH plus 1 on 3000, which is the load resistance, to get my total resistance, and then the output voltage is just that, and it's 3.413 volts. Okay, that's question 5.